I'm giving the first presentation about real-time operating systems written in Rust. That's a long title. I'm Elias Meyer, and I'm from Vappais. I made this as my bachelor thesis last year, so I'm giving you my bachelor thesis presentation enhanced with more slides. So yeah, I compared three real-time operating systems, which are TOC OS, Drone OS, and Arctic. First, something about myself. I started studying at 2016, so I'm now studying my 7th year here, working at Vappais since 2019. Graduated bachelor this summer, yay, and master hopefully next year. I will actually have tomorrow my first meeting about my master's thesis, right, Henry?
Yes, I agree.
Yeah, so before we hop into the realm of operating systems, I want to tell a few words about Rust and why Rust is a good choice of language to operating systems. Firstly, it does many checks as compile time, or in compile time, which is great, because then we can use the compile time for it and not the runtime. And it uses mainly the borrow checker for that. Also, Rust doesn't have any garbage collector, which means it's deterministic, it's predictable. The least thing we want from our real-time operating system is that sometime the garbage collector hops in and we miss the next deadline for our next task because the garbage collector is still running. So no garbage collector, that's really good for our real-time operating systems. Also, one of the main or key points from this whole thesis, which I learned, is that concurrency problems mainly derive from memory management problems. So if we solve the memory management problems, then the concurrency will be a lot more easier. And this is the case with Rust. It has a proper memory management, and that way it also has really great and advanced concurrency. Also, Rust has a command line tool called Cargo, which is used for package management, compiling, running the project, and so forth. It's really great and modern. How many of you can, with this slide, explain what are the basic tasks of an operating system? Like just simple, with a few sentences. Don't worry, I won't ask. Yeah, great, a few. So probably the main point is to use the scheduler. We could always program the program as a monolith or bare metal program. But as soon as our program has multiple things to do which need to be scheduled, it would be a lot easier to just use an operating system with a proper scheduler. The scheduler answers the question, if we have only one core on the CPU, but for example 4 processes, how do we divide this one resource for the 4 processes? By time slicing, but how? How much time does everyone get? Or for memory management. If we have one continuous block of memory, how do we divide this memory for these different processes so that the processes are not allowed to touch each other's memory? And lastly, an operating system also is an extendable framework. So if we start building our application on top of an operating system, it's always easier to continue developing that even further. So who knows, how does a real-time operating system differ actually from an operating system? Again, a few hand rises up. The spoken language real-time is often misleading because it is often understood that it's something really fast, something happening real-time. But actually, in the realm of operating systems, real-time means it's predictable, deterministic. So we want our scheduling to happen within a specified time frame, not before, not after. If it fails to get into that time frame, our task fails. Normal operating systems like Linux or Windows are not real-time. They try to excel in having the best possible throughput, and I don't really care if my Linux and LibreOffice wait 5, 50 or how many milliseconds. It doesn't matter for me as a human. That's why it's not a real-time operating system. But Linux can be made real-time using, for example, the preempt RT patch. Okay, now we get into the real-time operating systems. How many have heard about TOC OS? Some? Nice. This is the most complex of these three operating systems. It has the biggest hardware requirements because it depends on an MPU. It actually probably can be run without an MPU, but I don't know about that. So it mainly uses the MPU for protecting. That's the memory protection unit. It uses the memory protection unit to protect the memory. TOC OS also supports runtime loadable processes, just like normal operating systems. I can start one program and close another one on runtime, which is not quite, which does not, all RTOSes do not support that. And the processes may also be written in any desired programming language, not only in Rust. And because of these, TOC OS is probably suited for a bigger embedded devices like a sensor network, central handler, running multiple processes, which must be isolated from each other. Something about the TOC OS architecture. Oh, by the way, we have the next presentation also about TOC OS, so let's keep this as a short introduction to that one. But yeah, the TOC OS architecture can be seen here, and it's like in 2 or 3 layers. Processes, which are the user space processes, and then the kernel space. And the kernel space can be further divided into the core kernel and capsules. The processes represent the user space programs, like in Linux. They all have their own private memory segment, which is protected by the memory protection unit on hardware level. And they are also all run in separate threads, which the kernel schedules preemptively. Preemptive scheduling means that the kernel alone decides which processes get when the runtime. So if one process gets stuck in an infinite loop or something, it doesn't matter. All the other processes may still advance. Then the kernel space, it consists of from the core kernel and capsules, and it is written entirely in Rust. As you remember, the processes may be written in any programming language desired. And since the kernel is written in Rust, it is protected by the Rust type system. The capsules are on top of the kernel because they represent the drivers for the peripherals. For example, on a SoC. And since memory or dynamic memory allocation is by nature unsafe, it can fail anytime if we don't have any memory to allocate, the capsules are not allowed to make any memory allocations on themselves. That's why TOC OS provides for dynamic memory for the capsules in these grants. Each process has a designated space of memory from which the capsules may allocate memory if they need. Of course, they need to check that the process is still alive because the processes may die. So they need to check if the process is still there. Yeah. Okay, then the next operating system, Drone OS. Who has heard about Drone OS? A fewer hands rise up than before, which is predicted. This is a smaller operating system than the TOC OS. TOC OS does not, Drone OS does not need a memory protection unit, but it actually can use one if it's present on the chip. And since it does not need one, it has some special arrangements. Also, the tasks may not be dynamically loaded like in TOC OS, and they are entirely written in Rust, so it's just one binary flashed on the device. And like Rust, Drone OS has also this command line program called drone, which can be used to initialize a new project or to tweak some project, for example, dynamic memory allocation and so on. Let's see. The concurrency. SoC OS used time slicing in its concurrency, but Drone OS instead uses interrupts. The NVIC stands for the Nested Vectored Interrupt Controller. It uses interrupts rather than time slicing. And since Drone OS does not require a memory protection unit, it needs to make some special arrangements, which is that the previous task must relinquish the stack completely. So the only way that the processes do not tamper each other's memory space is that the previous task just clears its memory from the next one and stores it somewhere else. And the stack is also protected by placing it at the border of RAM. The concurrency in Drone OS consists of 4 building blocks: fibers, processes, threads, and tasks. Fibers are the basic building blocks. They are finite state machines. They work like generators, but they can have input values as parameters, and they can also return something. Yeah, they are used like generators. They can be yielded from. Processes are just specialized fibers. They can be stopped, and they're in synchronous. Threads are sequences of fibers which are managed by interrupt controller. This means that threads cannot be created on runtime. They must be created on compile time because each thread is assigned to a specific interrupt. But any number of fibers or processes can then be attached to these threads on runtime. So they are like dynamic linked lists, I think. And tasks are then the most user-space processes. They are mainly asynchronous functions which are running in a thread. Memory allocation. As we discussed earlier, everything should be deterministic in a real-time operating system, and malloc is not really deterministic. Drone OS solves this problem by dividing the whole memory segment into smaller segments, which can then be allocated and deallocated on runtime in a constant time. So the memory is just divided into segments which can be each individually allocated or deallocated, and that's why it's so fast. And for example, this configuration can be set by the drone command line tool. Message passing. This is my first and only one code example in this one. Drone OS has 3 types of message passing. It has the one-shot channel, which is used for just one message, a ring channel for multiple messages using a ring buffer, and also a pulse for sending flags, like something happened, do something. And it works like when the channel is created, it returns the TX and RX part. The TX part is kept in this thread, and the RX part is sent into the other thread, and then it can be awaited from to receive the message. Okay, now the last Artos, Arctic. Who has heard about Arctic before? I think a bit more than about Drone OS, which is interesting because Arctic is way smaller than Drone OS. Arctic is really just a simple concurrency framework written in Rust, and it stands for real-time interrupt-driven concurrency. It works using interrupts, just like Drone OS. It schedules tasks, which can be given a priority as an integer. It provides for a simple memory allocation using Rust's memory safety. And it also allows for simple message passing by calling explicitly tasks with arguments. So tasks are just functions which can be called by arguments, and that's how the message passing in Arctic works. And at this time, all ARM Cortex-M devices are fully supported.
Excuse me.
Yes?
I've been talking with the person who supervised the thesis, which Hello. This is working. This is working.
Yes.
Okay, so that framework was, I think, I'm not sure if I'm misrepresenting, but I think it was like mostly driven forward or made by a dissertation worker. And I am currently discussing with the supervisor of that dissertation worker about being able to offer the possibility of porting this on RISC-V, because to us it looks like technically simple. So we could do something like that. So just to point out that we have this also. You could do it if you want, but it's a big task. Something for maybe for a dissertation then.
Okay, this came a bit unexpected, but as a background, I talked about Henry about my master thesis, and in the spring, I think, as we discussed about this would have been one thesis topic to port Arctic on a RISC-V platform.
Yes, sorry about the interruption.
Yeah, as said, Arctic schedules tasks, and tasks are just normal Rust functions which are given these attributes like init, task, idle. It starts scheduling from the init task, which initializes the system, after which it continues with the tasks, other tasks, and as the tasks have different priorities set, it will start from the highest priority task and go downwards. And if there are no other tasks to schedule, it will finally start scheduling the idle task, which has the lowest possible priority. And the idle task could, for example, put the microcontroller into sleep so that it doesn't drain the battery. And the resource allocation, there are two kinds of resource allocations, local and shared. Local is meant for just one task. If one wants to, for example, allocate a big block of memory, not in the task itself, but for example in the main function, it can be done and passed on. If one would allocate a local memory segment and pass it down to multiple tasks, it would produce a compile time error because that would not work. And that's why there's the shared resource which can be passed onto multiple tasks. Passing a memory segment or a resource to multiple tasks introduces concurrency problems, and that's why the shared attribute internally will protect the memory segment with a mutex. Okay. Then for a quick recap, Arctic is the most simple. It's basically just a concurrency framework. TOC-OS is the closest to a full-blown OS, and Drone OS is a nice, friendly, user-friendly RTOS, which is kind of in the middle. It could use a memory protection unit if it's there, but it doesn't need one. Each of these are actually double licensed using Apache 2.0 and MIT license, so they can be freely used. Yeah, and since this one was my bachelor thesis, I also had my statistics there. So as you can see from the words or the pages, normal text or the PDF pages, it was a pretty long for a bachelor thesis. Yeah, thank you. Any questions? You can also come and ask me later if you want. Mm-hmm.
Curious about the Rust async ecosystem applied thing there, and how in general do you manage to work with async model there with all the interrupts, blocking calls, whatever else around?
Sorry, I didn't understand.
Maybe that's because I'm pretty far from embedded development, but generally, pain point of Rust and async Rust in particular would be blocking calls and all the things around. And interrupts, from my very naive idea, is also in a way dangerous in that term that it could block, or I don't know, just async process could in a way be stalled by whatever's going on the switching. So how do you basically work around those things, and how can you program Rust asynchronously in microcontrollers in RTOs?
That was a hard question. I'm sorry, I can't answer that.
Ignore me then, thank you.
I suggest you answer or ask Henry about that. Or does Henry know answer for that?
Yes. It's on.
It's
yes,
on.
great, cool, nice. Yes, I can answer that question. Please come to me afterwards.